So we are at the point that we are talking about chemical reactions and looking at balanced chemical equations. And we want to really answer those questions. How much am I mixing of my reactants? And how much product am I producing? So if we look at our balanced equation, and it's already balanced, we have these coefficients that are going to be mole ratios. Another way of saying this is for every 2 moles of hydrogen that I mix with 1 mole of oxygen, I produce 2 moles of water. So again, we're going to be using these coefficients to relate the different parts or the different substances in a chemical reaction. So the first thing we need to feel comfortable with is balancing those chemical reactions. And we'll go through some more in class, but I think the more challenging ones are the combustion reactions. So anytime I am reacting with oxygen, it's considered a combustion reaction. And if I have a organic molecule, so that's composed of carbon, hydrogen, or carbon, hydrogen, and oxygen, I am producing carbon dioxide gas and water vapor. So to balance this, since I have no metals, usually you balance the metals first, I'm going to go from left to right, and I'm going to save oxygen until last, because if I have an element hanging out by itself, it's much easier to balance it last. So let's start with carbon. We have 8 carbons on this side. We have only 1 on this side, so we need an 8 here. Okay. For hydrogen, we have 18 on this side. We have 2 on this side. So it tells me that we need a 9 here. Now, what I want to do is total up the number of oxygen I have only on my product side. For oxygen, I have, if I count the 16 here, and then I have 9 here, I have 25 total. So now I'm going back to my reactant side and saying all of my oxygen has to come from here. I have none here, so since this is an odd number, I'm going to initially say I have 25 over 2. Okay, so this only works because I have no oxygen here. I've isolated all of them here. But we know we can't have fractions as coefficients, so I'm going to multiply every single coefficient by 2. So in the end, I get 2C8H18 liquid, and I'm mixing that with 25 moles of oxygen gas, and I am producing 16 moles of carbon dioxide gas and 18 moles of water vapor. Let's go through one example. Now I'm starting with ethanol, and notice that I have oxygen in my formula. So I start with 2 carbons, so I need a 2 here to balance. I'm starting with 6 hydrogens, so I need a 3 here to balance. And if I total up my number of oxygens that I have 4 here, I have 3 here. Remember that this gets distributed not only to the hydrogen but also to the oxygen. I get a total of 7. Okay, so now I want to go to my reactant side and isolate all of the oxygens. So I have my total number of oxygens from the product side, 7. But I want to subtract out the oxygen here, so that way I isolate them all to just the O2 gas. So I'm going to subtract 1, and I get 6. So I need to account for 6 oxygens. Since it is an even number, I don't have to worry about a fraction. I put a 3 here, and now the equation is balanced. So again, our whole point of this chapter, or this part of the chapter, is figuring out how much do I mix, how much do I produce. So let's look at this problem and let's organize it. So have, want, and my get there. And for this problem it says, what is the mass in milligrams of oxygen needed to react with 78.3 grams of ethanol? So this is a question of how much do I mix. I'm starting with 78.3 grams of the C2. If we go back, H6O. So that's my ethanol. And I want milligrams of oxygen. Okay. Notice that in this case, since we're not just focusing on a chemical formula, we have a whole equation. When we say oxygen or chlorine or bromine, we have to know that it is the diatomic. So that's something to look out for. Now I'm going to ask myself the same questions that I normally do. So do I have units of grams next to anything? And I do for both, which tells me I need a molar mass of both. So for 1 mole of ethanol, if I go to the periodic table, it weighs 46.08 grams. And remember, we're labeling everything, even though I know it's a pain sometimes. We have units of mass also next to the oxygen. So I want to say for 1 mole of oxygen, it is going to weigh 32.00 grams. Right? So knowing that this oxygen is referring to O2 in a chemical equation for a chemical reaction is pretty important. It changes your mass. Am I starting with one thing and ending with something else? And the answer is yes for this. So I need to say that I need that mole ratio. So if I go back to my balanced equation, I have that. I am relating my moles of methanol to moles of oxygen. For every 1 mole of ethanol, we are reacting with 2 moles of oxygen. So let's put that in. For every 1 mole of ethanol, I can say 2 moles of oxygen if I look at my balanced equation. All right. So this should be 3 moles. Okay, I think we have what we need, so let's do a roadmap. We're going from grams of ethanol, and we know we can go to moles of ethanol using the molar mass. Then we can go to moles of oxygen, and from there we can go to grams of oxygen. So it looks like problems that we've already seen before. Let's plug in some numbers. So we have 78.3 grams of ethanol, and we want our mass in grams to be on the bottom, so that way we make things cross cancel. So 46.08 grams of ethanol for every 1 mole of ethanol. All right, we want our mole ratio. We're currently in moles of ethanol. Now we want moles of ethanol on the bottom, so for every 1 mole of ethanol, we have 3 moles of oxygen that we are reacting it with. And then we said for every 1 mole of oxygen, it's going to weigh 32.00 grams for oxygen. If we make everything cross cancel, we're left with the units we want. Not quite, right? So we also need to go to milligrams, right? We know that conversion factor. We know that for every 1 mole, for every 1 gram, you guys keep me honest, of oxygen, we have 1,000 milligrams of oxygen. So if we plug that into our calculator, and again, it's always good to look back at your want to make sure you have the correct units, we should get this. Okay, we can make our grams cross cancel as well. Let's look at another problem. So this answers how much do we mix? In the next problem, and let's organize it, we have what mass of CO2, okay, so we want grams of CO2 is released in the combustion of 2.00 grams of octane, okay? So we have 2.00 kilograms, actually, of octane, and you're given this formula on the slide where we balance the equation, so this is going to be octane. Okay, and we'll go through the same process. For this one, we have mass next to the octane, we have mass next to the carbon dioxide, which tells us we need a molar mass for both of those. For every 1 mole of octane, let's make sure we have the right formula, CaH18, it is going to weigh 114.26 grams. Okay, we need to do the same thing for CO2. For every 1 mole of CO2, it's going to weigh 44.01 grams. We're starting with one thing, we're ending with something else, so that tells us we need a mole ratio, and if we go back to our equation, we can get that mole ratio from the balanced chemical equation that we did before. So for every 2 moles of octane, right, we are producing or releasing 16 moles of carbon dioxide. And the last thing we want to do is look at our units. We have kilograms here, right? But in our get there, we only have grams, so we need that relationship as well. We want 10 to the 3 grams for every 1 kilogram. Always make sure the big number is with the smaller unit. For our roadmap, let's go ahead and do that as well. We're starting with kilograms of octane, and we can go to grams of octane. From there, we can go to moles of octane, and to figure out where I'm going next, I'm looking at my get there again and figuring out what relationships I can make. From moles of octane, I can relate that to moles of CO2, and from there, I can relate that to grams of carbon dioxide. Right? And then it just becomes, let's plug in the numbers. We're starting with 2.00 kilograms of octane. And we said we need to go to grams next. So for every 1 kilogram of octane, we have 1,000 grams of octane. And then if we follow our roadmap, now we're going to moles. We want that molar mass on the bottom to make things cross cancel. So we're done with those kilograms. We have 114.26 grams of octane for every 1 mole of octane. Okay, we get rid of the grams. We're currently in moles of octane. We're going to continue to go. It's kind of slanted, that's okay. For every 2 moles of octane, we are producing 16 moles of carbon dioxide. And our last step according to our roadmap is we want to go to grams of carbon dioxide. So for every 1 mole of carbon dioxide, we said it weighs 44.01 grams. So now the moles cross cancel, we're left with grams, which is what we want. And if we go ahead and now plug it into our calculator, we should get this, keeping in mind that we have to keep track of significant figures. So something else I would think about is kind of just the bigger picture of why we want to calculate the amount of product we should make. Okay, so think about it from an economical standpoint. If we're going to make some product, we want to make sure that we know how much we should make so we can figure out if it's a good reaction or not. Or the way we set up that reaction is in an efficient way to carry it out. So we want to think about our cookie recipe. All right, so I had you calculate how many cookies for all these different ingredients in your kitchen. So something I want you to keep in mind is when we're doing chemistry and calculating, it's just like cooking. Okay, don't worry if you don't know how to cook. That's okay. All right. So a few things to remember. Now, in the previous problems, I gave you the specific amounts, but let's say you have different ingredients and you have different amounts of those ingredients, but you want to figure out the maximum amount of product, like cookies, you can make. Now it becomes what we call a limiting reactant problem. And here are a few things I want you to remember. For each reactant, so I'm going to circle that. For every single reactant, if you're given an amount, you have to calculate the amount of product, just like the cookies. So whenever you're in doubt of where to go next, think about the cookies. Okay? You must calculate the amounts of the same product. So let's say you're doing a reaction where you have multiple products. You can use any of those products to figure out the limiting reactant, but you need to stick with the same product. The amount of product made is based on the limiting reactant. So you went through this exercise with the cookies and you found that the chocolate chips are limiting. I know it's sad, right? But those chocolate chips limit the amount of cookies we can make because we have to have chocolate chips in our cookies, right? For a reactant in excess, so whatever is limiting, your other reactant or reactants are going to be in excess. The amount of reacted substance that's in excess is also going to be based on the limiting reactant. So if I am limited by the number of chocolate chips to make my cookies, it tells me how many eggs I'm using, how much vanilla I'm using. It tells me how much of every other ingredient I'm using to make that limited amount of cookies. So here is a problem. So we have a nice lengthy problem that has all of the questions in there. So we're given a chemical reaction, and the reason I know this is because it says aluminum, and we're given an amount, is reacted with chlorine gas. We need to know that that's Cl2, and we're producing solid aluminum chloride. So this automatically tells you we're setting up a chemical reaction. First thing we want to start with is our balanced chemical equation because everything is based on it. And we want to answer a few questions. What reactant is limiting? What's the theoretical yield or the amount that I should make of my product? If experimentally I produce this much product, what's my percent yield? And then for my reactant that's in excess, how much is left over in grams? So all of these are good things to look at if you're setting up a reaction. So you have the answers for all of these. Okay, let's figure out how we get to those answers. So the very first part, A, is where we are trying to figure out what is limiting. All right, and before we do any of that, let's set up the equation. We're reacting aluminum metal with chlorine gas, and we are producing aluminum chloride, and you were given that it is a solid. So the next thing we need to do is balance this equation. We start with metals, so one aluminum. Then we go with the chlorine, so we would need a 2 here and a 3 here to balance, but then that changes our amount of aluminum. We need to put a 2 here to balance that. So you can't do anything unless you have the balanced equation. And then I'm going to go through and organize it. I have 73.6 grams of chlorine that I'm starting with. I have 65.2 grams of aluminum I'm starting with. And what I want is what is limiting. Okay, so for that we want to think of what we need. For both of these we need to go to amount of product. So I need to go from grams of chlorine, that's one of my reactant, ultimately to grams of aluminum chloride, my product, and then I also need to go from grams of aluminum to grams of aluminum chloride. We only have one product in this case, but again, if you have a reaction with multiple products, just make sure you're going to the same product. And we want to figure out which of these two is less. Okay, and that will tell us which one of these reactants is limiting. So now we want to think of all the pieces we need. So if I need to go from grams of this to grams of this, I need a lot of molar masses. So one is for the product. For 1 mole of aluminum chloride, it is going to weigh 133.33 grams. Okay, I need it for chlorine. 1 mole of chlorine is going to be 70.9 grams of chlorine. For aluminum, 1 mole of aluminum is going to be 26.98 grams of aluminum. And then I need those mole ratios. So for every 2 moles of aluminum, I produce 2 moles of aluminum chloride. For every 3 moles of chlorine, I produce 2 moles of aluminum chloride. Okay, so I have that, and I need to go from grams to grams ultimately, so I know I need to go from grams to moles to moles to grams. All right, let's do that for each one. We have 73.6 grams of chlorine, right? And now I know I need to go to moles next. For 1 mole of chlorine, it's going to weigh 70.9 grams of chlorine. And again, it's okay to go back and do your roadmap. The more work you show, the better. Okay? We said over here, for 3 moles of chlorine that I react, I'm producing 2 moles of aluminum chloride. And then for 1 mole of aluminum chloride, it weighs 133.33 grams. All right? And one question you may have is, well, could I have just stopped at moles? And yes, so I could have stopped at moles, and we can figure out which number of moles is less, but ultimately I need to go to grams anyway to calculate a theoretical yield, so why not just go to grams at the beginning? But either way is correct. Let's look at the next one. 65.2 grams of aluminum, and for every 1 mole of aluminum, it weighs 26.98 grams. We need our mole ratio next. Even though it's 1 to 1, 2 moles of aluminum is going to produce 2 moles of aluminum chloride. And for every 1 mole of aluminum chloride, it's going to weigh 133.33 grams. So aluminum chloride, right? And when we calculate those out, for the top we get for the bottom, I'm sorry, we get 322 grams of aluminum chloride. Okay, for this one, I'm going to put the number here, we get 92.3 grams of aluminum chloride. Notice that I went to grams of product. I'm going to say it over and over. And now we need to see which one is less. So this one is less. So that tells me, therefore, that reactant is going to be limiting. So is limiting. Right? Because it produces the lower amount of product. Now, since we already went to grams, this already takes care of B. So for B, since I already went to grams, my limiting reactant tells me how much product I'm making, since it limits the amount of product. So my theoretical yield is going to be 92.3 grams of aluminum chloride. So now when I go into the lab, I can figure out how much I actually make and compare it to how much I should make. This is the amount I should make. And that brings us to part C. So we want to calculate a percent yield, assuming that when we went into the lab, we actually made 82.6 grams of aluminum chloride. So the percent yield will be the experimental value. So always experimental on top. And we'll divide that by the theoretical, how much we should make. And since it's a percent, times 100%. And we get 82.6 grams divided by 92.3 grams times 100%. Make sure you put the grams in, even though they cancel. So when we do that, we get 89.5%. So this tells us something about that particular reaction or our lab skills, right? It's a pretty good yield. So the next question is, well, which reactant is in excess? And then by how much? All right. So since we only have the 2 reactants, since chlorine is our limiting, that means aluminum has to be in excess. And we want to figure out how much. Okay, so we know that we start with 65.2 grams of aluminum. Okay, so we start with that, but we're not reacting all of this aluminum. We have excess, we have some left over. So to figure out the amount of excess, well, we need to figure out how much we reacted. Okay, so we start with this amount. We need to subtract the grams of aluminum reacted. So this is the part that we need to figure out, and everything again will be based on the limiting reactant. So what we really need to do is go from grams of chlorine, so this is our limiting reactant, and we need to go to grams of aluminum to figure out how much is the minimum amount of aluminum we need to react with all of this chlorine. And then we'll have this value to subtract. All right. So if we need to go from grams of chlorine to grams of aluminum, we need molar masses for each of them. We need a mole ratio. And then we can set up the problem like this. We have 73.6 grams of chlorine that we're starting with. We want to go to moles of chlorine. So for 1 mole of chlorine, it's 70.9 grams of chlorine. And now our mole ratio, for 3 moles of chlorine, we need to react it with 2 moles of aluminum, and then 1 mole of aluminum is going to weigh 26.98 grams. Okay, and when we plug that into our calculator, we get 18.7 grams of aluminum. And the key is this is the amount that is reacted. Okay, so a very common mistake is to just stop there and say that 18.7 grams of aluminum are in excess. And that's not it. We're not done yet. We need to take our total, so 65.2 grams of aluminum total, and we need to subtract out the 18.7 grams of aluminum that we reacted. And what we produce, or what we get when we subtract that out, is 46.5 grams left over. Or another word for it is the amount of excess that we have. Okay, so this is our final value here. So there's one more way to set this problem up, and for those of you going to the second half of general chemistry, you'll see this a lot more, and those are ice tables. So initial change, and let's put an E here for equilibrium. So initially we put everything in moles, so you have the moles of both of your reactants based on the amounts given, and we haven't produced any product yet. And then what you do is you figure out which one is limiting by going to the number of moles here. Okay, we have a mole ratio to figure out how many moles of this we have. And from there we say, well, if this is limiting, we're using all of this up, and we are producing this number of moles of carbon dioxide and this number of moles of water, and we are reacting with this many moles of ethene. So once we do that, we can say, well, if I'm using all of this up, I have 0 moles at the end, but now I have moles of my ethene left over, and I could go straight from these moles to grams using a molar mass, and then I would already have my moles of product here, and then if I wanted a theoretical yield, I would just take these from moles to grams. So you don't have to use the ICE table for our class, but just do so you've seen it, all right? And then if you want to use it, you're more than welcome to. So if you wanted to calculate your theoretical yields, again, you would take them from moles to grams, and then you have the number of grams down here.